Hello everyone, in this video I'm going to solve some examples on Coulomb's law. Mainly we are learning about Coulomb's law and how it works and how we solve problems related to it. As we learned in lecture 2, Coulomb's law gives us the force between two charges. If we have like charges, they repel, and if we have opposite charges, they attract. Attraction and repelling forces are equal in magnitude and opposite in direction always, like we see in here or in here and so on. And here is the equation, what we call Coulomb's law. The force on one charge by the other, or vice versa, is equal to K Q1 Q2 over R squared. So it's directly proportional to charges and inversely proportional to R squared. Examples are pretty straightforward, but as always it could be confusing because we have a vector, we have to mind the direction as we calculate the total force and so on. This example, for example, is talking about how we have, if we have more than one forces, we show the direction of the forces and we calculate that total using vector addition. In this picture, if we look at charge 1 and the forces applied to it by 2 and 3, assuming they're all positive, we see 2 pushes on 1. If I call this F2, we call it F2 on 1 in here, and 3 also pushes on 1. If we call that F3, or F3 on 1, as they call it in this figure, we can add these two forces using head to tail, carrying 2 here as they show in this figure, adding it at the end of F3 1, and the vector combined the beginning of 3 to the end of 2 will be the total force vector. I can also use component methods or parallelogram methods. As we solve these problems, we will review vector addition. So vector addition and subtraction will be important here. So we did vector addition here to find the total force. Here's an example. We briefly look at this. I'm going to go over it again. A small plastic sphere with charge of -5 nanocoulomb is near another small plastic sphere with a charge of -15 nanocoulomb. I'm going to draw these spheres. Sphere 1 I'm going to call charge 1, and it has -5 nanocoulomb. We always use SI units, so I'm going to directly convert this to coulomb. -5 times 10 to -9 coulomb. And we have another sphere. Let's draw that blue. I'm going to call this sphere 2 with charge 2, and it has -15 nanocoulomb. And that would be equal to -15 times 10 to -9 coulomb. They have the same type of charge, so of course they will repel each other, and they do repel each other. As we look at the distance, we look at the distance between the centers of the spheres. Assume all the charge is located at the center, and distance R will be the distance in between them. Following the question, we see if the spheres repel one another with a force of magnitude 8.2 times 10 to -4 Newton. So the force is given to us, and I'm going to draw those forces. I'm going to draw the force applied by the red charge Q1 to be F1. We're going to use this notation. So everybody apply the force. If I look at the force applied by charge 1, Q1, I'm going to call that F1. That will be force on 2. And the force applied by Q2, I'm going to call F2. That will be the force on 1. Alright, the forces are equal in magnitude and opposite in direction. So I'm gonna go ahead and column F, just the equal forces, and calculate that force. Actually, we know that force. It's equal to 8.2 times 10 to minus 4 Newton. And the question is asking us what is the distance in between the charges. Writing down our Coulomb's law, force is equal to a constant we call Coulomb constant, or electric constant, electrostatic constant. Q1, Q2, I'm going to take the absolute value here. Once we decide the direction of forces, we don't need to worry about the sign of the charges. We took care of it. They both are negative, they push on each other, and we're done with that. And we need to solve for R here. Simplest method to solve for R algebraically is to switch F and R here. R squared then will be equal to K, Q1, Q2, absolute values divided by F, but we are looking for R, so we're going to take a square root of each side, and now on the left we'll have R. So R is equal to square root K Q1 Q2 over F. I'm not gonna put any sign, I'll just put the magnitude of charges, magnitude of force. If everything is in SI unit, your result for the distance will be in meters. And the constant K is 9 times 10 to 9 Newton meter squared divided by Coulomb squared. You don't have to worry about units as long as everybody is in SI units. Coulomb, Newton, and K is in SI units already. We'll find R, input everything in and find R. The answer should be 2.9 times 10 to minus 2 meters, or 2.9 centimeters. Here's another slightly more complicated question about two spheres. Let's read this. A small metal sphere has a mass of 0.18 grams. So gravity probably or might be involved in here because we're given the mass. And a charge of minus 26 nanocoulomb. Well, let's draw that sphere. I'm going to call it sphere 1 again with the charge 1. Minus 26 nanocoulomb, convert to coulomb again. 26 times 10 to minus 9 coulomb. And its mass is also given. I'm going to call it mass 1. To avoid too much cluttering on the figure, I'm going to put it aside here. 0.18 grams. But its SI units is kilograms, so I'm going to convert this to kilogram. Gram to kilogram is always times 10 to minus 3. So 0.18 times 10 to minus 3 kilograms. Okay, 18, not 19. And let's keep reading. It's 10 centimeters directly above an identical sphere that has the same charge. Alright, let's draw that. This is above another sphere that has the same charge. It's identical. Let's try to make it identical. Let's draw it red. So we'll have sphere 1, sphere 2, they are identical. So they have the same charge and same mass. Alright. And charge 1 is above charge 2. This lower sphere is fixed and cannot move. Let's fix it here. Fixed to the ground. Put some sort of stand. If the upper sphere is released, it will begin to fall. This gives us an information here. Since it will fall, gravity should be larger. So what's happening here is Let me show gravity. Green here. There is a force of gravity down, as always, right? Let's pull this a little bit. Force of gravity down, which is weight, right? We know this. That's mass times the gravity. It's called m1 times g. That's the weight of the first object. It's pulling down, and these two spheres are charged with the same type of charge, both minus, so they are repelling each other. I should have said here Q2 is equal to Q1. Let's put this here. So minus 26 nanocoulomb. Alright, so there is the force on 1/2 pushing up. That's the electrostatic force. So electrostatic force is up, gravitational force is down, and it's falling. That means gravitational force is larger here. That's a clue here. So let's call the electrostatic force Fc for F Coulomb. We don't know that, but we can calculate it. We know the distance, by the way. We forgot to put that in. That's 10 centimeters. Let's put that in here. So the distance in between 10 centimeters converted to meters, always divide by 100, so 0.1 meters here. Alright, so it's falling down, motion is down. We know from first term that if the motion is down, F net is down. Acceleration is always in the same direction as F net, so we'll take that down, and it's going down. What is the magnitude of its initial acceleration? Actually, question is asking us, what is that acceleration? So A, question mark. What we're going to use here is Newton's second law. Let's remember that. Acceleration times mass is equal to net force. One way of expressing this. Or acceleration is directly proportional to net force, inversely proportional to mass. So I can write Newton's second law as A is equal to F net divided by m. It would be m total if I have more than one masses tied to each other moving together, but I only have one mass here. Let's to specify it, let's call this A1 on mass 1, so we know which mass we are interested in. We can go ahead and call this F net 1, net force on the charge 1. I can pick any direction here, but easier way to go is to pick the direction of net force and acceleration to be positive. General consensus is down is negative, up is positive, but I can change it however I want to help me solve the problems easier. And the easier way would always be to pick the negative force F net direction or A acceleration direction to be positive. So we're going to go ahead and do that. We're going to take down as positive, then up will be negative. If you go the other way, take down as negative, up positive, it will also work. You'll get a negative A, meaning it's downward. But I choose to go this way. Always take the net force direction to be positive to avoid getting negatives, and just calculate direction the magnitude of A, and it will be positive. We already know it's downward, and positivity also shows that. Alright, so we're going to go ahead and do this. What we have to do is find those forces, because F net then will be equal to F net on charge 1 will be equal to the weight minus the Coulomb force. So we calculate these, input them in here, and input this F net in here. We already know mass 1. We'll get A from there. Let's do this. So what is weight, right? Weight is equal to, let's actually go to left here, so we'll carry them from there to the right. So weight is simple. It's the gravitational force between the mass 1 and the Earth, m1g. We all know what g is, 9.8 meters per second squared. I took down as positive, so it will be positive in my case here, and I'll put the values in. m1 was 0.18 times 10 to minus 3 kilogram, and g is 9.8 meters per second squared. I'm going to find my weight, and it will be in newtons. I took everything in SI units. My weight should come out as newtons. SI unit for force. And that should be, let me find my number here, 1.76 times 10 to minus 3 Newton. Now we will find the Coulomb force, or electrostatic force, or electric force between the charges, which is pushing on charge 1 in up direction, K, Q1, Q2 over R squared. Coulomb constant, K times 9 times 10 to 9 Newton meters squared over Coulomb squared. Q1, Q2 both minus 26. Let's drop the charge, sign of the charge. So I'm going to have 26 times 10 to minus 9, right, times 26 times 10 to minus 9. Notice here I'll be generally dropping the absolute value and the signs all together. Absolute value means we all take everything as positive. R squared, R 0.1 meters, take square of that. And we will have a value of this as 6.0884, let's leave that, times 10 to minus 4, not 6, 4 Newton. Let me rewrite that. Alright, now I have my forces, weight and the Coulomb force. Inserting them here. I'm going to find a net force. F that 1 when I insert them as actually I don't have a value for that in here. Let's directly, instead of keeping your weight and me calculating that, I'm actually going to directly enter them in the equation for A. So let's carry this here. I'm gonna use a different color here. So A1 is equal to F net 1 divided by M1, right? We decided that. Now I'm gonna put the values for F net 1. Weight 1 minus F Coulomb divided by M1. And put all the values. We're gonna have 1.76 times 10 to minus 3 Newton minus 6 times, not times, 6.084 times 10 to minus 4 Newton divided by mass 0.18 times 10 to minus 3 kilogram. Newton kilograms. A will be in SI units. Everybody is in SI units. And A should be 6.42 meters per second squared. I'm going to divide this part here. And here you go. It's down, it's negative. I already know that. I can put a note here. But it's obvious from my figure. I already know it, and I took negative. Sorry, we took down as positive. Let's just say down here. Again, if I take down as negative, A would be negative. But what matters is I know which direction it is. It is downward. I can call that positive or negative. Doesn't matter. It's my choice. All right, this is a nice question, actually involving previous information that we learned in last term. So it would be on the harder end of questions you might encounter. I want to talk about here in this question we saw that gravitational force is larger than electromagnetic force. But this is not a really good comparison because the mass of the Earth is huge and it's always making a difference in between the charges, mass force of gravity and force of electromagnetic force or electrostatic force. Sorry. What if I had them in the comparable values? What if I had two objects with masses and charges and I look at the gravitational force and Coulomb force in between them? How would they compare? This question is looking at that. We have two protons here, about 10 to minus 15 meters apart. This figure here is showing an overall size of an atom is about 10 to minus 10 meters. Protons are in the nucleus, actually. It's about 10 to minus 20 or so on average. So this is close to the size of an atom. Maybe a large atom could be this large. So we have two protons. Proton 1, proton 2, let's say. They have a distance in between them. And that distance, r, is times 10 to minus 15 meters. What is the comparison of the gravitational and Coulomb forces between them? So what happens here? Proton 1, proton 2, both are positively charged, right? Both actually has positive E. And I know what E is. 1.6 times 10 to minus 19 Coulomb. Both are protons and the mass of the proton, we know, I actually set them here, 1.6 times 10 to minus 27 kilogram. We have E here. So they have charges, they will be pushing on each other. Let me draw the forces with the same color as we always did. Equal in magnitude, opposite in direction. Notice also we always draw the forces, electrostatic forces or gravitational forces along the line joining the objects. Let me do a better job here. Pretty bad job. So we join the objects or connect the objects, and along that line we draw the forces. That helps us find the direction of the forces, and then we look at if they are pushing or pulling and draw the forces. So this is F Coulomb. I'm going to call it Fc. And gravitational force in between them, gravity always pulls or attracts, so they will be pulling on each other with the gravitational force. And I'm going to call it Fg. So we're going to compare these two forces. And let me delete that. I already have them listed, so I'm going to delete these here. Equations. Coulomb force equation. Let's first calculate Coulomb force. K Q1 Q2 over R squared, right? And our K is 9 times 10 to 9 Newton meter squared over Coulomb squared. Q1 Q2, if I'm multiplying Q1 and Q2, they will be the same charge, 1.67 times 10 to minus. So that's the mass. Go back. 1.6 times. Let's delete that. 1.6 times 10 to minus 19 coulomb. That's one proton, 1.6 times 10 to minus 19 coulomb. That's the other proton, all divided by the distance squared in between. Distance is 1 times 10 to minus 15 meters. If I do all these calculations, my Coulomb force should be about 230.4 Newton. Quite large. Now let's do the gravitational force. Right? Gravitation. Let's do the different color. And let's remember what gravitational force was. It's mg, mass times the gravity if we have them on Earth, gravitational acceleration. Or general equation is g mass 1 mass 2 divided by r squared as well. Mass 1, mass 2 would be protons. G is here, given here. Universal gravitational constant. Once we put all these in, 6.67 times 10 to minus 11, that's G, Newton meter squared over kilogram squared. Mass 1, mass 2 will be the proton's mass, 1.67 times 10 to minus 27 kilogram times the same thing, 1.67 times 10 to minus 27. Kilograms divided by the distance squared. And that's 1 times 10 to minus 15 again, meters squared. If we do all these calculations, we will find the gravitational force to be equal to 1.86 times 10 to minus 35 Newton. Now look at the difference. There's a huge difference in between. You can look at their ratio to see how much larger electrostatic force or Coulomb force than the gravitational force. So if I divide Fc by Fg, I'm going to find about a value of about 1.24 times 10 to 37. Now this distance is a bit larger than general distance for atomic nucleus, but close to it. So there's a large electromagnetic force or Coulomb force, electrostatic force, sorry, and very small gravitational attraction. So actually among the forces, we have 4 fundamental forces. Gravity is the weakest. Now I have a question for you. We know that protons stays in the nucleus together, but they strongly push on each other. Gravitational attraction doesn't do much. How do they stay together? What makes them stay together? Do a research about that. The last question I want to look at is a complicated in terms of geometry only, but idea is simple. We have 3 charges and we're going to find a force applied to one of them by the other 2. We have to find the forces and add them and so on, and there isn't really a specification of easiness of angles and so on. So in terms of those, it's kind of hard, but not really. We'll be okay. So let's try. 3 spheres are fixed in places as shown below. What is the total force on charge C? So this dude is charge C here. Total force. Let's call this F, total C. Can give it any name. What I'm going to do, I'm going to call the forces, draw the forces on charge C, and name them. I'm gonna call the force applied by charge A to be FA, charge B to be FB. And as we see, charges are all, not all, never mind. These two dudes are positive, right? Let's go back. Let's actually. So this guy is positive, and the C is negative, so they will be pulling on C. Let's draw those forces. A will be pulling on C. Just like that. I'm gonna push this a bit. Alright. I'm gonna call it FA. That's an electrostatic force, electric force, or Coulomb force. Not FC, FA. That's force applied by A to C. Let me pick another color here for B. I'm going to call the force by B on C to be FB. It's also pulling because B is positive and C is negative. Charges are not to scale, but I can guess the forces are not to scale, but I can guess the force applied by B will be larger because its charge is more and its distance is smaller. But I'll just draw them, not to scale, just the directions, FB. And as we can see, there is no geometry to ease our work here. We have an angle here we have to find. I'm going to call that angle theta. There's not a the forces are not perpendicular to each other, not in the same direction or opposite direction. So this is one of the hardest type in geometrical terms we might get. So we have to draw XY system. Let me actually do that differently. I'm gonna draw it maybe let's try with a thinner line, a different color. As always, we take the horizontal axis to be X and vertical axis to be Y. Let me extend this Y a little bit. So Y and x-axis, and these will help us define the direction of forces and force components. Once I draw my Y and draw my coordinate system, I'll take up as positive. In these cases, always stick with the convention: up positive, down negative, right positive, left negative. And I'm going to look at my forces. I'm going to find the total of these forces, and I don't really have anything to ease my work, so I have to find components. I have to go component approach. And let's remember what we do in components method. We find all the components, find FAX, FAY, right, and find FBX and FBY. Then we add to find the total. And as we find X and Y components, they are also symbolized in vectors that are showing how A and B effects on C, so we have to mind the direction. And let's actually look at those. I'm going to draw components of A, actually with red, so it will be agreeing with the vector. As we can see here, this should be A's X component, FAX, to the left. I don't want to make it really cluttered, and again, it's not to scale. I know it's to the left, but because what we do is we draw lines from A onto the x-axis, and wherever it hits, let me actually make that a bit better looking. Wherever it hits the x-axis, it's where where the x component is. So I'm gonna stop it here actually, so it will be more close to scale. So this is FAX and it's negative, it's to the left, so I'm gonna put a note here, FAX will be negative. I figured it out from the figure. FAY is also negative. If I notice, it's down and down is negative. So let's draw it on this FB. I have an FAY here. When I look at FB, I see that it has no x component, it's only y, so FBX is 0, and I also see FB will be equal to FBY, and it's down, it's also negative. Now I'm going to go ahead and find them, and I'm going to say then F total x will be equal to FBX plus FAX, right? And I'm going to show these as vectors because I'm not showing their directions yet. And as I add them, I'm going to put the signs. FB was 0, I know that, and FAX is negative. And once I find FAX entered in here, I have the x component of the total force. F total y will be found similarly. I'm putting it as vector. It could be up or down, right? And it will be FBY plus FAY. Again, directions matter, so I'm putting my vector hats. And I figured that they both are negative, so I'm going to have minus FBY minus FAY. If I add them, I'll get a negative number. They both are downward. Now we're going to find these. FA. Let's go with FA first. FA is equal to K, QA, QC. The force A applies to C, right? QA, QC divided by, let's call this RA squared, distance of A to C. And that would be this distance here, folks. And we don't know that, which is why we say this question would be on the harder end. But we can easily find that because we have a right triangle here. We have one side, the other side known, and we're looking for the third side. So Pythagorean, and we can easily go ahead and find. We'll say RA squared is equal to 0.3 squared. Well, that's meters squared plus 0.4 and take square root, right? Or simply RA is equal to square root of 0.3 squared plus 0.4 squared. That will be in meters, and that will be 0.5 meters. So we can insert that in here now. I forgot to mention the charges are in microcoulomb. Converting to coulomb from micro will be always minus 9 microcoulomb is minus 9 times 10 to minus 6 coulomb. The same goes for A and B. So we're gonna put these in here. K is the electrostatic constant. Let me put it at this corner here. 9 times 10 to 9 Newton meter squared over Coulomb squared. Putting all these in, find an FA. So what we're gonna do is input K, input QA and QC, drop the signs, we find the direction of forces, no need for the signs. We're gonna get a force for FA to be 1.29. I'm going to put some more decimals here until I reach the end, so I won't be losing a lot of precisions. 1.296, yep. It has an X and Y components. I have to find those. FAX, let's remember that as well. As we're finding components, we always look at the angle that my force or any vector I'm interested in makes with the x-axis, and I'm also interested in the smaller angle. So I'm interested in this alpha angle here. I have to find that angle, and I can easily find it using this angle here. So if I find theta, alpha is equal to 90 minus theta, because I have a 90-degree angle here. Don't fret, my friends, because I picked this question because it involves a lot of stuff and I want to train you on that. So I'm going to find this theta, and I have 90-degree angle here. Alpha plus theta is 90, so alpha is equal to 90 minus theta. And finding that theta is not very hard actually. If I go tangent, this is my theta here, opposite over adjacent, right? So tangent to minus opposite over adjacent will give me that angle. Let's find that here. Theta is equal to tangent to minus 1, 0.3 over 0.4, and that theta comes out as 36.9 degree. And with that, alpha is about 90 minus theta, 36.9 degree, comes out as about 53.1. You can take that as 53, but I'll put some more precision here. Now I can find AX. FAX is FA times cosine alpha. Insert FA, insert cosine alpha, you'll have FAX. And that will be equal to 0.778. 0.8 would be a good approximation, but again, I'm going to keep some more precision here. And we know it's negative. You can, if you like, you can put the negative sign here. But I always go this way. So it's negative. Keep that in mind. FAY. It's FA sine alpha. Again, let's remember this. Alpha is always the angle with x-axis, and we usually use a smaller angle. We go with geometry to define the directions and calculate the components as FAX, FA cosine alpha, and FAY, FA sine alpha. Once I do those calculations, I'm going to find y to be 1.04 over 0.36 to be more precise, and it's also negative. So these two guys are negative, down and left. FB is only along y, so once I found FB, I'll have FBY, x is 0, it'll be easier. Let me use another color for FB. FB is equal to K, right? Charge B, charge C, divided by RB squared. We know charge B, charge C. This guy here would be our RB, right? Distance from B to C. And once we input everything, we're going to find a force as let's see what I have here, 3.038 upon 3.04 Newton. And that's down, that's negative, that's also equal to FBY. Only along Y, FBX is equal to 0. Now what we're gonna do is input everybody in here and find these values. Once we do that, this is simply FAX, it's negative, it's 0.778. And once we put FBY and FAY, we're going to get a value of minus 4.074. So we have F total Y and F total X. I want to open a new page here to talk about what we do after that. So let's see. Here's my friends. I'm gonna draw XY system again. And I'm only gonna talk about the total force in this one. Okay, let's go. That's Y. This is a bit. Let me try that again. Okay, this. So Y, X. Remember, we found F total Y to be, let's do it again, minus 4.074, so that's down, and F total X to be minus 0.778, about minus 0.8, right, or 0.78. Let's skip 2 decimals, Newton, and minus 4.07 Newton. I'm gonna draw those on the system here. F total X. Let's draw straight lines to the left. And F total Y is down and significantly larger than F total X. So let's try that again. Okay. All right. Okay, that's the best that I could do. So F total X, F total Y. That's what we found. We showed the directions. They both are negative. Then what we do is we go parallelogram method. Actually, here we draw a parallelogram, and the diagonal is the total force here. And how we find the total force? This is the total force, Ft, or FTC, right? The total force on charge C. Remember, we have a charge C here. And we're looking at the total force on it. Now, this total force will make an angle. Let me call this gamma because we used alpha, beta. Physicists loves Greek letters, right? Gamma. The angle it makes with the x-axis can also be found, and F total easily can be found as long as we know x and y components. This should be F total x. And here it is. F total is equal to, from Pythagorean, F total x squared plus F total y squared in square root. That's it. And here is why, because when we draw this parallelogram here, this is the x component, this side is actually the y component. Let's draw that straight line. And we have a right angle here. And the right angle gives us the total vector with Pythagorean. That's it. You don't have to draw this figure, but I am drawing it to show you and help you understand what's happening there. Why F total is that. You learned this, but we're reviewing, right? So input everybody in, and you'll find the F total. And it should be, let me see, what is the number I have for total force? 4.15 Newton. And that's the direction, that black vector here. If I'm asked to find what is its direction, how to describe it, I will say it makes the angle gamma with the x-axis, with the negative x-axis, right? This is negative here. And that's equal to always tangent to -1, the y component, opposite over the x component. Easily I can find that. Keep in mind though, that's angle is always the angle the force or the vector makes with the x-axis, but the smaller angle. What I mean by that is, notice the smaller angle alpha here. There's also with the minus x-axis, so as I describe it, I will say it's the gamma, sorry. The gamma is the angle between minus x and the force, total force. Many of you gets confused about what about this angle. You can also use that, but it's easier, a lot simpler to use the smaller angle. So we will always use the smaller angle, and that's how we find it. So that's, if I do this, tangent to -1 f total y over f total x, I'm gonna find that angle to be 79.2 degrees. And it makes sense because the y component is significantly larger than the x component, and I couldn't even draw them to scale. Pretty much fy is 4 and fx is 0.7, so quite larger, and it will have a large angle with the negative x-axis here. Alright, see you on the next video.